Okay, folks, I thought I'd show you the start of example B. So in this case, I chose to let u equal 2 plus x. That's this expression right here. And then a consequence of that is that the u is just equal to dx. Okay. Now, that's not a big deal. We know this. Okay, I'll be able to replace this with the square root of u du. Great. But I have this x squared factor now that I need to take care of. Well, because u is equal to 2 plus x, I could actually solve this expression for x instead, which is kind of doing a backwards sort of substitution. So then if I went ahead and solved this for x, I'd find that x equals u minus 2. Okay, so then we can take the x squared and replace it with u minus 2 squared. So in place of this x squared here, I put u minus 2 quantity squared. And then there's the square root from the original integrand. And then in place of 2 plus x, I put u. So in place of 2 plus x, I put u. And then in place of differential x, I put differential u. Okay. You've got all the tools to solve this, and I did not finish it out, but I went ahead and just reminded you you could FOIL out that expression right here. And then you could go ahead and distribute this u to the 1/2. Remember, square root of u is u to the 1/2. You could distribute this u to the 1/2 to both of these terms. And now you're in a position to integrate this termwise. Now you won't be done once you do that. You'll need to then do the back substitution step, but that gets the ball rolling. And I apologize I didn't give you enough room to complete this. Okay, so I'd like you guys to do C and D. There are no new tricks in C and D. You've encountered those tricks already. And so let's move on to example 7. Okay. So let's go ahead and first evaluate this antiderivative. Notice this is not a definite integral, but we're getting ready to do definite integrals with u-substitutions. So we've got the natural log of x over x dx, and I notice that an expression shows up as it does its derivative. If you're having a hard time seeing it, you may want to write this optional step, the natural log of x times 1 over x dx. Now it's a little bit clearer that something shows up, natural log of x, as well as its derivative, 1 over x. So in this case, I'm going to let u equal the natural log of x. So the consequence of that would be du is equal to 1 over x differential x. Notice that in this case, we're back to having a perfect substitution. I've got the factor 1 over x, and I've got the factor differential x, and so I'm just going to, in place of those two factors, write the factor differential u. So I think now we're ready to write this. We get the integral of, in place of natural log of x, I'm going to write u, and in place of 1 over x differential x, I'm going to put du, which is about as a simple integral as we could now encounter. We'll just use the power rule on this, and we get the antiderivative of u is 1/2 u squared plus c. Now we need to replace u with the variable we started with. U was holding the place of the natural log of x, so we get the natural log of x quantity squared. Careful, that squared's outside the logarithm, so it needs to be indicated as such, plus c. Okay. So we're now going to go ahead and solve this. We're now going to go ahead and solve this definite integral, using the combination of this step plus what we already know. So the antiderivative of the definite integral of 1 to e of the natural log of x over x dx is equal to, well, we just found out that its antiderivative is this expression here. So it would be 1/2 natural log of x quantity squared, and we choose the constant 1, the constant 0, okay, evaluated at the lower and upper limits of integration. Just as a reminder, let me put the x equals here, and in fact, just to even further remind you, I'm going to put the x equals here, and I recommend you do that for this problem. So now we can evaluate this. We get 1/2 times the natural log of e quantity squared minus 1/2 times the natural log of 1 quantity squared by the fundamental theorem of calculus, which is what took us from here to here, and now we're just finishing evaluating that. Well, the natural log of e is 1, and the natural log of 1 is 0, and so we end up with 1/2 for this. Now, what I'm going to do now is do a combination of part A and part B in this single example C here. And this is how you should, the way I do it in C is how you should do it going forward. So A and B were just meant to be illustrative of how we get an answer of 1/2. And now I'm going to show you how to do a u-substitution, as I say, without doing the back substitution step. Okay. So here we go. So we've got the antiderivative of 1 to e of the natural log of x over x dx. Like before, I'm going to let u equal the natural log of x, so that makes du equal to 1 over x dx. That part's unchanged. What's going to be new now is I'm going to adjust these limits of integration. Okay? Let me just remind you, this said when x equals 1 up to x equals e. But I'm going to shift this function to a different variable. So I'm going to shift this integral to a different variable. So we've got the antiderivative of u differential u, just like we had before. But now I'm also going to adjust the limits of integration. Notice I didn't put anything here yet. Okay? So these need to also be in terms of u. And that's the new material for this problem. I need to adjust the limits of integration to be in terms of u, not in terms of x. Well, here is the formula that I came up with that relates u and x together. So notice that when, what's this first x value I have? When x equals 1, well, u is equal to the natural log of 1, which is equal to 0. So my lower limit of integration is going to be 0. Similarly, when x equals, now I pick the upper limit of integration. That upper limit of integration used to be e. Well, u is equal to the natural log of e. So u is equal to 1. So notice what we did here. This is different. We started with the original definite integral. Everything was in terms of x. We did the u-substitution. Nothing too exciting there, just like we've always been doing for the u-substitution. But not only did we adjust the expression inside the integral, because it's a definite integral, we need to also adjust the limits of integration. So this is the key new step, is to simply say, hey, I can use this formula right here to switch the limits of integration from x equals 1 to u equals 0. And again, I'll use this formula right here to switch the limits of integration from x equals e to u equals 1. So now I've completely shifted this problem. It's absolutely essential that you remember to adjust your limits of integration when you do a u-substitution on a definite integral. And you may think that that seems hard, but notice one thing that this does for us. Now when I apply the fundamental theorem of calculus part 2, notice that this is all set, ready to be evaluated, and there is no back substitution step. So now we'll just say that's 1/2 times 1 squared minus 1/2 times 0 squared, and just as before, we arrive at the same answer, but we never had to do a back substitution step. And this is how I want you to evaluate indefinite integrals moving forward. Okay? That was tough. You're going to get some more practice on this, but for right now I'd like you to try number 8 for class tomorrow, and let me know if you have any questions.